start. Our first speaker is Bruno Lanson with the XRD, and here we are.
Thank you, Georgios. So yes, I think I will try to stay on time and try to teach you something. So the first point, for those who have some old guys like I am, probably recognize in the title of this presentation something like a book that was published 45 years ago, something like that. And you will see that I will take examples from this book because I think it's still a fairly good way to learn. And this is still a book I'm essentially using on an everyday basis, not for everything, but for some stuff. That's something we can clearly still use and use fairly commonly. I don't know if you had, and what I will try, the main thing I modified in the title was to include not only clay minerals, but also any kind of defective lamellar minerals. And you will see that depending on what I will try to illustrate, I will use phyllosilicates or some other phyto minerals. Just because sometimes it's easier for me, so I will probably use LDH example, I will use lamellar oxides example and things like that. So I don't know if you had time to go through the slides that were made available to you, but essentially I will skip the whole first 30 slides. Just one point here, there are just basic knowledge on the clay mineral structure. The main point, if there is only one to keep here, is that essentially all clay minerals are based on the same building blocks, sheets of tetrahedra sharing apices here, and the other apex with octahedral sheets, and octahedral sheets that may contain any kind of divalent or trivalent cations. And that, from that simple information, you can clearly see that there is essentially all phyllosilicates will have essentially the same dimension in the layer plane, and that their main difference will come from the layer to layer distance, which is controlled by how many sheets of tetrahedra or of octahedra, and on the nature or presence of interlayer cation or interlayer species. That will be the main difference we will have between any of the clay minerals. And this will make a very strong condition for their identification. Who has done X-ray identification? So essentially, the first thing we will have to know here is what are the parameters we can measure using X-ray diffraction, and what kind of information we can obtain from these. So clearly, the main, to answer these first two questions, is that what we are measuring when we are using X-ray diffraction techniques is that we are measuring interplanar distances within crystals. This means that we have to have repetition, to have something crystalline, if possible periodic or almost periodic, and that these interplanar distances are typical of periodicity we may have within crystals. We have distance between these planes here, we have distance between these planes, we have distance between any of these planes. And because these distances are intracrystalline distances, they are in the order of magnitude of fractions of angstrom to tenths of angstroms, essentially. And because we will use to be able to measure these distances with some kind of accuracy, we will need to use a beam that has essentially the same wavelengths as the distances we want to measure. Why that? First thing is that the way we will measure these distances is that we will be using Bragg's law. And what Bragg's law says is that if we want to measure this distance between two planes of atoms within a crystal, we will have the incident wave coming in, and clearly the difference of path between the wave coming in here and coming in here will be these two distances here. And this, if this is d, here you have the theta angle, which is the same as the incident angle from the wave to the plane here, which is exactly the same as you have here. And this is clearly d sine theta, this is d sine theta. So the difference of path between these two waves is 2d sine theta. And if this is a multiple angle of the wavelength, you will have contrastive interference at the end, and you will have diffraction peak. 110 years ago, this was worth the Nobel Prize of Physics. Now it's just basic geometry, and you will learn that in 5th grade or something like that. So clearly, if you are measuring that, so here you have how we measure that physically with the diffractometer, where we have the sample, where you have your sample, where you have your crystal here. And the X-ray source from where the wave is coming, and you are measuring that with the detector. You're measuring this outgoing wave here. So this is how we measure that. For those of you who have never seen X-ray diffractometer, this is the one we have in my lab here, where we have very basic configuration with X-ray tube here, the diffractometer which is controlling the angles is the wheel behind. You have the sample, in this case we have a sample chamber where we are able to control relative humidity, temperature, etc., etc. And you have the whole set of detector here with a lot of slits in between. I'll get back to that. From the tube, you have high voltage generator, which is useful to generate these waves, and I will just show you how this is working, and then everything else is below that. So how things are worked, these are slides I just added last night, actually this morning very early. How this is working. So what you have here, you have this high voltage here between the cathode and the anode. And essentially what you are doing is that you are heating a filament of tungsten that actually expelling electrons to this target, which is copper, which could be whatever source of you may think of. In this case, this is for rhodium, if I remember correctly. And you will have emission lines. You have steady and almost continuous background, which is perhaps shallow, and you have typical lines, K alpha and K beta. And these are the lines we are actually using to use X-ray diffraction. If you think of that, clearly you are, at the same time, you are actually getting electrons coming out from this usually tungsten filament. Clearly what you will do is you will also evaporate at the same time your tungsten filament, which means that with time, you will get small deposit of tungsten on your anode here, meaning that you will get these emission lines for copper, cobalt, whatever you have, plus emission line from tungsten also. And just to show you what could be the main problem with that is that here I have a sample, in which a clay sample, in which I have quartz here, I have calcite here, and here I have a small peak that was identified at that time as anhydrite. Fit was not perfect. Clearly there was a problem that breadth was much, the fitted peak was much too broad compared to what was measured, etc., etc. But if you redo the exact same fit, accounting this peak not for anhydrite, but for tungsten emission line for quartz, you will end up, and this is 1% contribution from tungsten, you see that you are able to fit almost perfectly both copper, K alpha for quartz, first line of quartz, and also tungsten line for quartz. Tungsten line for quartz. So this is important because this could also lead to keep in mind that your system could get older, as we are old, but in this case, we are not emitting more and more. We're trying to decrease our emissions. And here, the problem with the X-ray tube is that you are getting not only what you would like here, but something that has nothing to do, not nothing to do, but it's also clearly an emission here from the tungsten that was deposited on your anode. So here, clearly, you may have these additional lines, and this is just to keep in mind, just because this could lead to complete misidentification, that I don't have any anhydrite here, I just have quartz with tungsten emission. Another possible source of X-rays, which is becoming more and more common, is clearly synchrotron sources. How do these work? You have an injection here, and after that you have electrons or positrons spinning around essentially at the speed of light. And to make them turn, to be able to do all these turns, you have usually magnets. It could be just one Begning magnet, or it could be wigglers, which is an alternation of permanent magnets that would go back and forth. And it's just as when you are driving, there is centrifuge force in the turns, which means that because the electrons are already spinning at the speed of light, they cannot go any faster. So what they have to do to avoid to go faster, because they cannot do, is just to emit energy, and they emit energy in the X-ray range. The advantage of these lines here is the order of magnitude you get from emission from copper or molybdenum tubes. This is what you can get from synchrotron sources, which means that we are somewhere in between. For the second generation here, we have already at least 2 orders of magnitude, and for the most recent one, we have up to 8 or 10 extra orders of magnitude more brilliance when using synchrotron sources compared to X-ray tubes. It's not really as convenient, it's much more difficult to get one in the lab. But this is clearly an alternative you can consider if you have to make quick experiments, if you have to make time-resolved experiments, if you have to make experiments with extremely small quantities of material, if you have, for any kind of reasons, you may consider the opportunity of not using the X-ray tube you have next door in your lab. This is probably the first thing you want to do, to be able to know at least what you are going to look for, but you may also consider the opportunity to get this information from synchrotron facilities. So once you've overcome this emission of X-rays source, here what you usually have is a powder. In this case, it's oriented slide, and we will see later why we are preparing oriented slides for clay minerals. Your sample stage, and here you may have any kind of detection system. This is 1D detection system with energy resolution. Clearly, what you want to, if you think about what we showed before here, what you want to have from your sample here is essentially the wavelengths you've introduced, which means that what we want to use is one of these 2 wavelengths here for the X-ray tubes, or for synchrotron sources, you want to use one of the energy or one of the wavelengths you have selected, and you will be selected these by using monochromator just to select one specific wavelength. You may be able to use a wide beam or at least a pink beam for some specific characterization like lower experience, etc. But most of the time, you will select one wavelength, and you will select these wavelengths depending on the monochromator that are available on the specific beamline you want to use. And the other point is that you will also, from that, and you can see that depending on the energy, you will be selecting. If you want to work here at 20 keV or 10 keV, you will probably use one of these, not these ones here, because energy will start to be decreasing a lot. And if you want to work at higher energy here, you will probably go to APS or whatever. And this is just going to be depending on which type of experiment you want to do, and especially depending on how far you want to go in the reciprocal space, which is essentially depending on how crystalline is your material. So here, to select the energy, you have either to select it on lab machines. There were different ways that have been proposed over time to be able to record only the wavelengths you are interested in. The first one that was introduced was to introduce filters in the beam path, where you were able to remove K beta, for example, from K beta alpha plus K beta emission line, if you want one of these two emission lines. It may have been also at some point some monochromator, again, put in the outgoing beam path that would allow with a very crystalline material. It could be graphite, it could be germanium, it could be any kind of material here, monocrystalline if possible. That was used. And more recently, but these are already more than 30 years old, there were detectors that would allow you to select the energy of the outgoing waves and to select only the ones that have interacted elastically with your material. Why is that? Is that because if you record everything coming out from your sample, you will record what you are interested in, elastic interaction that would give rise to diffraction. There is no modification of the wavelengths, but you will also record everything that goes with inelastic interaction with your sample here. And inelastic interaction is the first one you may think of is just fluorescence. What you are doing when you are measuring on your scanning electron microscope or electron microprobe or whatever, you are interacting with high energy beam with your sample to generate fluorescence from all atoms that are present in your sample. In this case, you are not recording information on the periodicity within your crystals, but you are recording intensity about what types of atoms do I have in my sample. I don't care where they are, but I want them to be present. Is that clear for everybody or not? If not, raise hand. Okay, which means that in doing that, clearly, what we are doing, or what we are choosing to do when doing X-ray diffraction is that we are just interested, or at first interested in periodicities that are present in the crystals. And then we will see that there is a way to actually get information not only on what is the periodicity, but what are not only what atoms are present where in the structure, but which kind of atom are present where in the structure. So this is how we measure this information, and the information we will extract. This is typical diffraction pattern we can record on soil sample in this case, if I remember correctly. And you have diffraction peak at different angles. And all these angles, all these intensity measured at different angles correspond to different d values. And all these d values are periodicities that are present in the sample. And the next thing is to actually try to say that, so I have a peak here at 4.26 angstrom, this is 3.44 angstrom, etc., etc. And from that, I will try to compare all the positions I have recorded in my samples to a series of databases that record all for all known phases or all known minerals, in our case mostly, that will be able to record all the different lines that should be present for, in this case, quartz. So I have this 4.26 angstrom peak, 3.34, etc. And all these correspond to different periodicities that are present in my sample. So from that, you can see that one extremely important parameter here is position of diffraction lines. Because position of diffraction lines tell you that you have such and such distances that are present in your sample or in your material, and that these can be compared to ICD database or COD database or whatever the database you want to use, just because you are working with mineral species, you are working with organic species, you are working with whatever, but you can always compare them to these databases. So clearly, the first information you will get is peak position. And if you look in the book I showed you earlier, the first thing, and I will get back to that later, the first thing you will see is tables of position for all possible clay minerals and all possible polytypes of these minerals. So this is what was done almost a century ago to actually be able to determine the structure of layer silicates. And in this case, so this is from that specific book here, but this was used from Mauguin and by Linus Pauling a couple of years later to actually be able to determine the structure, in this case of micas, a specific variety of muscovite. It was quite impressive that even a century ago, they were able to record diffraction data up to 0.55 angstrom, which means that they were able to record X-ray diffraction data all the way to, if you are using a copper wavelength, something like 120, 140 degrees. They were able to record that on extremely perfect results that would probably give for modern diffractometers, they would completely blind your detector for these lines, for sure. But this was quite impressive at that time. So, and from that, they were able to determine unit cell parameters and essentially the motif of the unit cell. And you can recognize here the sheet of tetrahedra and the sheet of the octahedral sheet that's lying in between with dioctahedral character with vacancies here. Just to make that clear, I will just also show you another type of structure I will use. It's just composed. So this will I will use that for lamellar oxide, lamellar hydroxide, layer double hydroxide, and the basic structure is always the same for all these minerals. It's just, you just think about an octahedral sheet with no tetrahedral sheet on either side. In this case, so this is just blue side structure. You can recognize magnesium, OH2, just perfectly. So it's trioctahedral characters. There is no vacancy here. And you will see that even depending only on position, position can be used for much more than just defining unit cell parameter, or unit cell parameter can be used to much more than that. These metal hydroxide, lamellar ones, can be, you go from calcium hydroxide all the way to iron-free oxide and hydroxide. You have the protonated part of the structure, but you keep essentially the same. All these, except for iron-free one, are known minerals. And you can see that depending on the ionic radius of the octahedral cation here, you have an almost straight line. Regression coefficient is quite good as a function of unit cell parameter, as a function of ionic radius, which means that you're not only able to determine unit cell parameter, but if you are somewhere in between here and you know that you have manganese 2 and cadmium 2 plus, you may be able to determine or to roughly estimate relative proportion of one or the other. If you have something between iron 2 and iron 3, and if you know that you have only iron in your system, you may also be able to have an idea of oxidation degree of your system. So here you may see that this is valid for the A parameter, which is the in-plane parameter that gives the size of the unit cell within the layer plane. But if you are looking at the C parameter perpendicular to the unit plane, or C star, it should be, regression is poor, to say the least. Why is that? If you get back to this, the A parameter, the first one, is depending on this. On the in-plane distances. And in-plane distances will clearly depend only or mostly on interatomic distances within shear. But from one to the other, you see that bond length will be much weaker, and that probably there is no direct link between the size of the cation here and the distance from one layer to the next one. And this is clearly what we see here. From in-plane, for in-plane distances, or for, we have extremely good regression line. If for the one perpendicular to the distance, we have much weaker regression. So far, I've tried to show you what's possible to use for only position, but clearly you know that depending on what you will be recording data from, you will have sharp peaks, you will have much broader peaks, etc., and that these peaks, so, will come from, essentially in the case of clay minerals, from their small crystal size. And small crystal size could be due actually to two things. One is size, and the other one is strain. And these were also described a long time ago. Both of these were described 80 years ago, roughly. And it was possible to determine both size here and strains. Strains meaning that you have small variation of the distances we are measuring within, from one crystal to the other, or within a given crystal, and that we were able from the peak breadth to get that information. This was, I will get back to that. So this is typically what we are seeing here, is that for this peak, this is typical diffraction patterns, polar diffraction pattern from Memorialite in this case. And you can see that we have extremely broad peaks We have some sharper ones, but we have broad peaks. And that this is the full width of half maximum intensity of these different peaks. Clearly here, you can see that peak breadth is fairly high here. Minimum value we have is 0.6 degrees, meaning two things. Meaning that this breadth is probably intrinsic. I would not say intrinsic, but yeah, peak breadth is quite high. There are two reasons or two possible reasons for that. One is due to your sample. We have small crystal size, we have a lot of strains, does not matter, and this results in large or broad peaks. The other reason that could be is that you have extremely large opening of your slits on your diffractometer, because on your diffractometer, you can see that, so this is the exact same picture I showed you before, except that it's schematized. Here you think about the, it's not better, about the tube being here, the sample being here, and the detector being here. And in the beam pass here, you have lots of slits usually. And depending on the opening of these slits here, you may clearly control the breadth of the peak of the diffraction peaks you record from your sample. Clearly, the objective when you are doing that is to have slits that are small enough to minimize the broadening due to the instrument. Usually these cannot be tuned. So the slits here and so the slits here, these are fixed slits that are built in your instrument, but you are usually able to change these slits here, divergent slits, anti-scatter slits, and receiving slits. And you are able to play with these three blue slits to decrease or increase the size, the breadth of your diffraction peaks. But if you are measuring, so if you are measuring quartz powder, it's clearly interesting to try to reduce the size of these slits, the opening of these slits, to improve as much as possible the resolution of your instrument and to get as much as little as possible what we call instrumental broadening due to the wavelength distribution at first and then due to the opening of these slits here. If you are working with clay minerals, here, from your most of the peak breadth is actually due to your sample, due to small crystal size, due to disorder in this case also. And clearly, there is no point to decrease as much as possible the opening of your slits, because this is the minimum breadth you will be able, whatever set of slits you will be using. I was hoping to be able to record data to show you that before I come, but we actually broke the two diffractometers we have in the lab, and I was not able to do so over the last 2 weeks, essentially. But essentially, depending on the opening of the slits here, you may decrease the opening of the slits, and you will always record the same peak breadth here, just because this breadth is actually interesting to your sample. But what you are doing when you are decreasing the opening of your slits here is that you are allowing less and less beam to go through and to irradiate your sample, which means that on the other end here, you are recording less and less intensity. There is just no point in doing that for polycrystalline samples. For polycrystalline sample, you can use larger or more open slits just to allow more beam to go and to irradiate your sample, just because at the end, what you are interested is to get more intensity, and because the peak breadth here cannot be reduced by decreasing the opening of the slits. Is that clear to everybody or not? Another point that's related to that is that here you have peaks that are about 0.6 degrees wide. There is no need to record diffraction data every 0.01 degree. This would mean that you have here more than 60 data points to collect the upper half of your peak, which is just useless, completely useless. Which means that you can use much larger step size to record diffraction data from polycrystalline samples such as this one. Yes?
When you say much larger, what would you recommend? What is the step size that you would go with? And what is the slit size that you would recommend modifying?
So I will just repeat the question because probably people don't understand, did not hear you. The question here was how large can we get step size and how large can we get slits opening?
What would you recommend, not how large?
What I would recommend, what's usually recommended is to have between 7-10 data points to get at half maximum intensity, which in this case would mean that to be able to describe even this peak here, if you have a step size of 0.04, that's plenty enough. If in addition to that you have quartz crystals, this may change. Because in this case, your quartz crystal will be, depending on slits opening, you will have peaks that will be 0.2 degrees wide or 0.15 degrees wide. In this case, if what you are interested in is getting relative proportion, for example, of both, it may be interesting to have to record for the best crystalline to decrease step size to be able to record good data even for the best crystalline sample, for the best crystalline mineral in your mixture. And
so you have to paraphrase, if you have a mixture of poorly crystalline or big crystals and well crystallized or narrow crystals with sharp peaks, you would choose the step size that would allow you to have 7 data points up to the max of, up to that half max of the
divide that
of the smallest,
yeah,
the most narrow peak that you are worried about.
Yeah, exactly. And as to the opening of your slits, I wouldn't do that for every sample I would have, but something I would recommend is from some typical samples you have is just to play with that at first, which means that go from very sharp, very small opening and so very low intensity, and increase that, and to start to say at which point you think you may see a very clear browning due to the instrument. For this type of diffraction data, you can open them a lot. If you have, again, quartz plus something else, I'm using quartz because this is usually one of the best crystalline mineral you have in your sample. In this case, you may want to decrease that a bit. It's always a trade-off. Clearly, when you are decreasing the opening of your slits, you are decreasing the amount of intensity you have from your sample. You are improving the resolution, but you are decreasing the amount of intensity.
When you're adjusting the slit sizes between the 3 slits, are you doing so uniformly across?
What you are doing is you're doing it uniformly for divergence and anti-scatter, because these are perfectly symmetrical on each side of your sample. And after that, you have a resolution slit that you usually also increasing, or you're doing it in the same direction.
Sure.
But it's not strictly proportional.
Okay, thank you.
So this means that it's not because you are going to an X-ray lab that have been doing X-rays on minerals for decades or whatever, and that have been always using the same kind of condition. If you come with a sample like that one, and that they have been using sharp, small sizes, etc., or what you want to have is the best type of diffraction pattern from your specific sample. And if you want to investigate this sample in detail, maybe it's worth to discuss with the people in charge of the diffraction machine and tell her or him that I want this and that specific, or I want to determine what are the best conditions for my sample, because I want to have the best diffraction data for this specific sample. And this is extremely important. It's not because people have been doing things, I would not say in the wrong way, but doing that for decades, that they have to continue on your sample. This is what essentially written here, that depending on your sample, there is no need to have extra small step size, just because in this case here, you can clearly see that peak breadth is clearly intrinsic to your sample. And it will be interpreted as such, and that in this case, instrumental setup may be adapted or should be adapted depending on what you want to do. And clearly the next step is to try to get this size and strain information from your diffraction data. And this is essentially what was done also in the Rietveld approach. Again, that's nothing new. This was brought up about 60 years ago, where they were able to, or when Hugo Rietveld was actually able to interpret in this, at the time it was essentially devoted to neutron data, but to analyze the profile. And in his mind, profile was mainly the distribution of intensity about Bragg's peaks, to show that it was possible to obtain both the size and the strain depending on the evolution of peak breadth in this case as a function of diffraction angle, mostly because they do not broaden the peak in the same way as a function of diffraction angle. One is a function of cos theta and the other one is a function of tangent theta. So this was done both by Berthaud and by Williamson and all at that time, and this plot is still used. And you can see that even though it was proposed 60 years ago, or even more than that for the different, or for the, I would say, automatic refinement of this parameter, is still topic for current literature, how to best determine or best differentiate size and strain contribution to peak broadening. So it is possible, not saying it's easy and straightforward. And depending on the sample you are dealing with, it may actually be quite complicated to do so. So if we go back to identification of clay phases, and especially what is specific for identification of these clay phases, if you remember what I told you in the very beginning, when I skipped the first 30 slides, was that the unit cell wasation of all phyllosilicate is essentially built out of the same building blocks, tetrahedral sheets and octahedral sheets. So there are small variation of the size of the octahedral sheet we've seen. We see example of the metal hydroxide lamellar structures, but essentially all these peaks will have the same dimension in plane. And this is this position here for HK bands here that are the same, going from alwazite to sarcodite to kerolite. And you can see that, so we have small variation of this position. No battery in this one anymore. Let's keep back the other one. So these peaks here have small variation. You can see here that we have much larger diffraction angle here compared to these ones. This is just what we will use later to differentiate dioctadal clay minerals from trioctadal ones. But essentially, you can see that this position is the same. This position is roughly the same. This position is roughly the same. This position is roughly the same. Meaning that in plane dimension, for all clay minerals here, will be the same, just because the building blocks are just the same for all clay minerals. Meaning what? Meaning that what we are interested in is mostly 0-0 reflection that are characteristic of the layer to layer distance. Okay? How do we do that? We usually do that, so what we are interested in is to measure the thickness of the layers, which means to measure the thickness of these sheets here. And the easiest way is to have them settling like that on your substrate. In this case, you are able to measure directly the thickness of all these sheets. You are not interested in having crystals like that, which means that what you are interested in is to prepare what we call oriented preparation, oriented slide or whatever, just to be able to measure only 0-0 reflection. And you can see here that I got rid of most of these H-scale reflections. The only ones that are left are somewhere here. When doing that, you have to think that during sample preparation, you have tried to get rid of random orientation. So you have tried to get rid of crystals being oriented with all possible orientation within your sample. Meaning that if you think about what we did at first was to try to compare all possible periodicity present in my sample to the database. Here you wanted at first to remove most of these periodicities, which means that databases such as ICDD are just not relevant for clay mineral identification. Most of the peaks that are shown here are just not present in the diffraction data I recorded because I wanted at first to exclude them by preparing oriented slides. Here, to be able to do that, what do we usually do? We are usually trying to, at first, to extract what we call the clay fraction, clay size fraction, whatever. And we usually do that on the basis of size fractionation. Just because the proportion of phyllosilicate, of clay phases, is much more important in the less than 2 micron, in the less than 0.2, in the less than whatever fraction you choose. This has no real importance. But really, and the fraction of non-clay minerals is usually lower. There are two advantages of getting that proportion of non-clay minerals to a minimum. The first one is you increase the diffraction intensity from minerals you are interested in, phyllosilicates. And the other one, you are trying also to improve as much as possible the orientation. Just think of this as being a quartz crystal. Orientation is not as good as it was if you have no quartz crystal. That's the first reason. So that's the main reason behind size fractionation. But usually when you are performing size fractionation, you are also performing a series of treatment before this size fractionation. You are trying usually to remove iron oxide, you are trying to remove organic matter, you are trying to remove calcium carbonate. Why? One thing you have to think of here is, when was this treatment proposed? And most of these treatments were actually proposed in the 1950s. Just think about what was the intensity of X-ray tubes at that time, and what was the ability to remove, for example, fluorescence of iron from your data. So you can always say that I want this, I want to remove that, because presence of iron oxide will change the density of my material, which will not be 2.72, but will be 2.73, because I have 0.2% of iron oxide. Who cares? Who cares if in the end you have less than 2.0.5 micron, or if you have less than 1.95 micron fraction? Nobody. So depending, so I'm not saying you should not do that, you should not try to remove iron oxide, but maybe now we have ways not to remove iron fluorescence without losing too much intensity. One example is to use energy resolve detector. In this case, you're just counting the good photons and nothing else, but you're counting all of them. You don't have to have diffraction, you don't have to have a filter where you will lose 50% of your intensity. You will be able to measure all diffracted intensity from your sample, but nothing else, which is, in this case, you have no way to, you are not losing anything by recording a sample in which you have both clay minerals and small iron oxide glued on your clay minerals. We just change slightly the size fraction you will be looking at, but usually you are reporting less than 2 micron fraction, not less than 2.00 micron fraction. For organic matter, it's essentially the same, except that in this case, you may have some, especially in soil samples, aggregation, formation of aggregate between organic matter and your phyllosilicate. In this case, it may be interesting to remove organic matter to disperse as much as possible your clay fraction. What about calcium carbonate? What's the interest of that? What will happen if you put a sample in which you have phyllosilicates plus calcium carbonate in water? You will dissolve calcite. If you dissolve calcite, you will create ionic strength in your suspension. If you create ionic strength in your suspension, you will flocculate everything. And in this case, there is no way you will be able to separate less than 2 micron fraction. So clearly, if there is one of these treatments to be kept, is removal of calcium carbonate, assuming that you have calcium carbonate in your sample. So maybe it's worth grinding your sample at first, grind part of your sample at first, record bulk diffraction data. How much calcium carbonate do I have? A few percent, I need to remove them. Known, I don't care. No need to perform treatments that you don't need. This will save time. And depending on the number of samples you may have, it may be interesting to save time. So next is size fractionation, and we explain why this was important. Then you may be interested in saturating interlayers. This is especially true for expandable clays, smectite, vermiculite, things like that, to ensure that you have, as much as possible, the same cation in all interlayers. What's the interest of that? Again, remember that identification is so far mainly based on peak position. Here I have the exact same smectite with different cation in the interlayer, recorded all at the same relative humidity. And you can see that peak position is not exactly the same. Meaning that if I base my identification only on peak position, here I have 6 different samples, 6 different minerals, which is not the case. I have one mineral with different interlayer cations. This may look, why bother about that, but think about now you are working on smectite to light transformation, let's say, something like that. This evolution of peak position could be well interpreted in terms of different proportion of E-light. No, it's 100% smectite, just the interlayer cation in the different smectite interlayers is not always the same. Meaning that if you want to be able to follow, so this is one example, but another example could be, for example, to think about possible intercalation of either other metal cations or other organic cations in smectite interlayer or other organic molecules. And in this case, you want to make sure where you start from. And for this, making sure of where you start from, saturating all interlayers with one single cation is clearly something you want to do. Another thing you may want to do related to that, so here I have the same smectite as before, only lithium in the interlayer, and recorded at different relative humidities. Again, think that your identification is based on peak position. And depending on relative humidity, this lithium saturated smectite has a wide range of position just because we are changing hydrogen state from 80% relative humidity, where we have 2 planes of interlayer water molecules. Over most of that range here, we have only 1 plane of interlayer water molecules. And here at 0%, we start to dehydrate completely lithium cations. But again, if you think about, if you want to measure small evolution of the presence of another cation in the interlayer of another molecule in the interlayer, you will need to have one single cation and to be able to record that at one relative humidity. It's worse than that. Here I have moionic smectite. I think it was calcium saturated. And here we recorded diffraction data starting from 0% relative humidity here. We increase relative humidity to 94% relative humidity here. So we are going from essentially dehydrated smectite here, smectite with 1 plane of interlayer water molecules here, smectite with 2 planes of interlayer water molecules here, smectite with 3 planes of water molecules here, and then back to 2 planes, 1 planes, and we were not able, without heating the sample, to dehydrate it completely back to completely dehydrated smectite. But if you think about doing the same thing with water absorption isotherms here, I'm starting from this point here, which is essentially this one. I'm going up with 1 plane of interlayer water molecules, 2 planes of interlayer water molecules, 3 planes somewhere here. And then I go back to 2 planes, 1 plane, and I cannot reach the completely dehydrated. So we have, in all cases, the same behavior as exactly as we see here. But we also see that there is an hysteresis. And these are 2 diffraction patterns that were taken on the same homoionic smectite at 12% relative humidity, one along the adsorption branch of the isotherm, this one here, and one along the desorption branch here. And you can see that they are not the same either. Which means that it's not only, if you want to assess small variation of layer to layer distance about incorporation of nucleotide of specific cation or specific organic molecule, you need one interlayer cation, one relative humidity, and you want to make sure of where you are, on which branch of the isotherm you are. It's not that complicated. I mean, equilibration of this at a given relative humidity is quite fast. So to make sure that you are here at 12% relative humidity on the desorption branch, this one, what you want to do is just put that everything to 60, 70%. Let's wait for 15 minutes, half an hour if necessary, and then bring everything back to 12% relative humidity. And in this case, you are sure you are here on the red curve, not on the blue one. Obviously, this is when you start to want to make some accurate estimate of is there any evolution of my sample because I exposed it to this molecule or to this condition or to specific. In this case, clearly, if you measure one sample in this condition and the other one, change has been huge. No. I'm just not measuring it in the same conditions. Another thing that if you think about identification based on peak position for clay size fractions, I mean clay size fraction meaning extremely minute crystal sizes. These are just calculated diffraction patterns, but this is just to show you the effect of decreasing crystal size. So the first effect you see when decreasing crystal size, when decreasing the size of the current scattering domain, is that you see browning. This is the first effect you can see here. But associated to this browning, because your diffraction patterns that is calculated here is a convolution of interference function, and the interference function controls the breadth of the peak and of structure factor, which will modulate relative peak intensity. And in this region, in this low angle region, the structure factor is strongly decreasing, which means that when you are broadening the peaks, you are making them go uphill, I would say, and you have a very strong change of peak position for the exact same periodicity, 12.5 angstrom, just because we have decreased a lot the size of the crystal. In this case, if you want to compare your sample, one sample from the other, something you may want to check is that the change you are seeing here is just a function of broadening of the peaks. In this case, you can see here that I am able to measure the exact same periodicity in this region here, just because in this region the structure factor is essentially constant. So I have no shift of the diffraction peak depending on peak breadth. But in this region here, I see that strength. I see that change. So is the change I'm seeing in the low angle region related only to peak broadening, decreasing of crystal size, delamination, or is it really due to something specific, to a change of the layer to layer distance? So this is not to convince you that there is no way to deal with all these if there was no way, I would not be here speaking with you. It's just to say that if we want to deal with X-ray diffraction identification of clay minerals, we have to be aware of these different possibilities, of these different factors that may influence or not the diffraction data we may obtain from the samples we have. And if we want to assess some specific and small or variation, or to assess them as precisely as possible, we have to make measurements in the right condition, to prepare the sample in the right way, and to measure it in the right condition. And I've exposed some of that. So clearly, if you have recording diffraction data on a mica, you may not want to do all that because you won't be, this could be an influence. You may have delamination at some point, but for example, cation exchange or control of the relative humidity should play a minor role, I would say, at least for dipole micas, etc., etc. It may not be useful to use all this care for all samples, but in some cases, if you want to assess minor variation of the smectite interlayer composition, it may be worth actually using all these. Another thing that's related, which is fairly well known, but some of you may not know it, is that, so this is the expression of the structure factor I was speaking of. And in the structure factor, what's written here is that we essentially have an information of how many atoms of what nature here, the what nature is this scattering factor written here, are where in my structure. The where in my structure is essentially X, Y, and Z conditions. So if you think about the chloride, you have a 2-to-1 layer. So tetrahedron, octahedron, tetrahedron, in which I have variable content of iron. And in the brucite layer, the interlayer brucite-like sheet, octahedral brucite-like sheet, you have no iron. And in this case, depending on the amount of octahedral layer, octahedral iron in the 2-to-1 layer, you have pick the same positions. Periodicity is the same always, but you have completely different distribution of intensity depending on the iron content. This information about the about iron content, you are probably able to obtain that from electron microscope analysis, SEM analysis, whatever. So this you are probably able to constrain and to make a simulation, assuming that you have the right amount of iron in your chloride. Just may not be that simple because here I have assumed chloride in which I have total iron content constant. I always have 3 iron in total in the 2 octahedral layer. I just change the distribution between the one in the 2-to-1 layer here and the one in the brucite layer. The 3-to-1, the 3-0 here is exactly the same as the black one here. But you can see that depending on where I put the iron, I will have again the same peak position. The periodicity is again the same, but completely different distribution of intensity. So now I put a lot of constraint difficulties, whatever you could call that. Most of these are related to sensitivity of physico-chemical condition, but that's also why we are interested in these minerals. A lot of structural defects. Structural defects could be this time of isomorphic substitution.
We also have, in a lot of cases, coexistence of phases with rather similar composition. You may think about coexistence of discrete light and IS minerals. We have what we call interstratification, coexistence within the same crystals of different layer types with different layer-to-layer distance. You can recognize here mica-like layers and expandable layers. And if you want to have a thorough identification of your mineral, of the mineral present in your system, in this case, probably the best solution is to compare what you have measured in your sample and what you think what you have in your sample through simulation. And obviously, depending on the amount of time you will be able to have a good fit to your data, or you will say that what I think I have in my sample represents something like X% of what I really have. And I know there is room for more and for improvement, but at least I have compared to make the initial simulation and to compare that. That's quite fast. To improve the quality of the fit, this could take much more time. And again, the point here is not to say that. So what I will try to show you now is to show you a series of examples where it's possible to have this kind of improvement and kind of fit. It's not always necessary to go as far as what I will show you, but at least try to compare what you have measured from your sample and what you think you have in your sample. So one reason of why where we were interested in mixed layer structure, in interstratified structure, is that the first reason is that they are extremely common type of order disorder in lamellar structure. It's available, it's present in phyllosilicates, it's present in phyllomanganate, which is manganese hydroxides, layered manganese hydroxides, LDH, sulfides, graphite, whatever you can think of. So probably the most famous example is that of smectite, at least for clay people, is that the smectite to illite transition, where we have a change in diffraction patterns as a function of expandability, of presence of the relative proportion of expandable layers or expandable interlayers in a series of crystals containing both non-expandable and expandable layers. And this was described a long time ago, and it has been a source of research for probably late 1960s to early 2000, something like that, until people, because it was thought to be a kind of a paleo thermometer, and clearly the problem is that the thermometer was not accurate in a range that would go for the interesting range from essentially 25 degrees to 100 degrees, which is not really what you want for a thermometer, especially in these kind of settings. It has been used later on for any kind of purposes. It was shown, for example, for the interstratification of the different interlayers, inorganic interlayers in smectite, with alternation of expanded interlayers or hydrated interlayers with containing essentially sodium and water to something that contain essentially potassium here. And at some point, you can see that we have a continuous change of position from those corresponding to pure dehydrated potassium to pure hydrated sodium. It was also investigated for partial exchange of inorganic sodium cations by organic cations in an effort to prepare amphiphilic materials having both hydrophilic properties of inorganic interlayers and hydrophobic properties of organic interlayers. the same one to this is another example. Just think of this KV here scale as a 2 theta scale. It's essentially the same, just the diffraction setup was a bit different with a fixed angle and variable energy. And in this case, you can see that we start from LDH having chlorine as the interlayer, ending up with the same LDH with tartrate as interlayer, anion in this case. And again, in between, we have 50-50 in mixed layer with a regular alternation of chlorine and tartrate interlayers. And again, this is mainly the purpose of this is to have polyfunctional material with, in this case, chlorine interlayers bringing mechanical resistance and tartrate interlayers bringing flame retardant properties to these materials. So how do we detect this interstratification? The first thing, when you are doing X-ray diffraction on this kind of mixed layer or interstratified minerals, is that you have non-rational series of reflections. And what does mean non-rational series of reflection? It means that if you multiply the D00L, so D001, D002, 3, 4, 5, by L, you always obtain something different from D001. Clearly here, if you multiply this position by 2, you will have something which is larger than D001. If you multiply this one by 3, you will end up with something smaller than D001, which means that there is no way to find a unique set of unit cell parameter to match all positions. And this non-rationality comes just because you have no periodicity in the crystals. If you have a random interstratification, which means that you have a random alternation of these different layer types, you will have peak position somewhere in between reflection corresponding to periodic light in this case, and periodic light, so periodic red and blue component. And you can see that you have always peak position of the mixed layer. In this case, I have 70% red, 30% blue, and peaks corresponding to this random interstratification are always located somewhere in between periodic blue and periodic red, periodic blue, periodic red, periodic blue, periodic red, periodic blue, periodic red. And peaks are somewhere in between, and there is no way I can find a set of unit cell parameters to match all these positions. So this is again nothing new. It was rationalized almost 80 years ago by Jacques Mering. And Victor Dritz redid the same thing more recently for non-basal reflection, meaning HCl reflection, and we will see that a bit later on. You will see that later on. So this, just think also as this position in between blue and red, blue and red, blue and red, blue, red and blue here, as a way to predict the type of layers that are interstratified. Here I added position of kaolinite in green. And clearly I have nowhere a peak, maybe here, but there is also a blue line that's standing here. And I have nowhere a peak somewhere in between green and blue, or between green and red. Meaning that even from that simple diffraction data, I can assume that I know I have an interstratified structure. I'm unable to find a unique set of unit cell parameters to match all position. And most likely, the different layer types that are interstratified are red and blue, and not red and green or blue and green. So not only am I able to say that I have interstratification, but I'm able to say that I have interstratification between this type of layer and this type of layer. Is that clear? Not clear? So from that, clearly there has been a set of methods that were proposed based on peak position. Again, peak position is something easy to measure and determine from using X-ray diffraction, to try to say that if I have interstratification between blue and red layers, depending on the position of this peak here, and for different type of interstratification, random interstratification is the dashed line here, I should have something going from essentially pure and periodic red to pure and periodic blue here, going along this line. And from this identification, I should be able to determine a relative proportion of red and blue layers. No problem. And this has been the basis for a lot of identification methods that were proposed from the late 1970s to early 1990s, essentially. Another very specific character of diffraction patterns coming from this interstratified structure is that you see here that I have broad peak, sharp peak, broad peak, broad peak, which is something completely different from what you expect from size and strain browning, where you expect a steady increase of browning as a function of diffraction angle, as a function of cos theta, and as a function of tangent theta, but roughly a steady increase. Here I have large or broad peaks, sharp peaks, broad, etc., depending on how far reflection from blue and red components are from each other. If they are far from each other, I have a broad line. If they are close to each other, I have a sharp line. So this was generalized later on by Dritz for non-basal reflection. This is what I just told you. And what I told you earlier is that what I would like you to get from that class, I showed you all the pitfalls you may encounter, all the precaution you may want to take to avoid them as possible, etc., etc. And also, probably what I think would be important would be to try to, you've made an identification here saying that most likely what I have in this case is interstratification between blue and red layers. From that, you will be able to estimate how much blue, how much red, and how they will stack on top of each other, etc., etc. You will get an estimate, probably based on one of these methods here. And from that, you think you have identified what you have in your sample. Just make a simple calculation, trying to match what you have measured from your sample and what you think you have in your sample. These were examples that were performed at the time so still in the same book by Bob Reynolds, here with Dewey Moore. And you can see here that they have compared what they have measured from their sample here to what they have calculated from the sample. And you can see that in some cases it's working, in some cases it's not. Here you have additional peaks that are not present. You have peaks that are clearly have not the same shape or profile that from what they measured, etc., etc. So, but at least they were honest enough to say, this is what I have measured, this is what I think I have in my sample, and here is the comparison. And they show it. They could just say that I have whatever. This was probably periodic series, so I have 50-50 sample, 50-50 interstratification of smectite with 2 planes of interior molecules and mica, and that's it. And show no comparison. This is another example where you can see that here, if you compare peak position, they are roughly the same, except maybe in this region here. But if you want to superimpose both patterns here, you can clearly see that here I have very strong differences in peak position. And this is the high angle region where I have most accuracy on peak position. And also here you can see that I have discrepancy between what they have measured in black, I think. Yes, what they have measured in black and what they have calculated to as their identification in purple. So there were room left for further identification. This was 55 years ago, and they did a fantastic job at that time. No question about that. But there were clearly some room left for more interpretation. So the point here is that if you really want to go further than that, what you will need is to get quantitative profile fitting, and that matching peak position or matching whatever parameter you have measured in your sample with what you think you have in your sample is not sufficient. If you really want to know exactly or accurately what you have in your sample, you have to go through this quantitative profile fitting. And what I will try to show you with a few examples next, we'll try to show you that it's actually possible to get this quantitative profile fitting even on natural sample. So this is one example from soil. It's from western France, I would say. And clearly what we are seeing here, that we have peaks at 14.3 something, we have peaks at 10, we have peaks at 7.18, we have difference between diffraction data recorded after on calcium saturated and after air dry condition and after ethylene glycol solvation. So I probably have here chloride, I probably have mica contribution, I probably have kaolinite contribution, and I probably have here a mixed layer containing at least mica and some expandable interlayers, and we will even consider that the presence of chloride in that interlayer. Meaning that if I want to fit the data of this diffraction data, what I have is chloride, elite, kaolinite, you use 2 contributions because of size distribution, and a mixed layer or interstratified structure containing elite, chloride, and smectite layers. And with that, I'm able to reproduce most of the peaks from my diffraction data. And I'm happy with that. But if you look a bit more carefully here, there is very strong discrepancy between what I have calculated in red and what I have measured, the black crosses. The same here, the same here, the same all where these arrows are. Which means that I have fitted or I have understood most of what is present in the well crystalline but part of my sample, but I am still missing some intensity, scattered intensity here, that's also coming from my sample. So we spent, or to be honest, he spent some time to try to understand where this could come from. And because this was soil sample, he decided that maybe this is just a very fine grain size fraction that could have different diffraction properties. And what it said that rather than extracting the less than 2 micron fraction, he extracted some even finer size fraction, and he extracted the less than 50 nanometer size fraction. And when doing that, the less than 50 nanometer size fraction provides the blue diffraction pattern here, which provides intensity essentially where we were missing intensity before. Why bother? Because this less than 50 nanometer size fraction represents 1/3 of the less than 2 micron fraction. And if you are interested in the reactivity of this soil, probably this is the third which is most reactive. Just think about sugar. You are using powder sugar or candy sugar to sweet your coffee. Powder sugar works much better just because it's finer grained. So we did, or he did the exact same thing. He tried to fit this data. He was able to fit the data with different interstratified structures here. It doesn't really matter what they are. And he assumed that this fraction here accounts for about 1/3 of the less than 2 micron fraction. And in this case, we are able to have a reasonable fit of the data in all regions, including these regions here. Not saying it's perfect, but the model was complicated enough to stop at some point. Why? The question you may ask now is that maybe with that many contributions, it's possible to fit an elephant. Yeah, but if you remember correctly, what I showed you in the very beginning for this specific sample is that we had 2 diffraction patterns. One after calcium and air dry condition, one with calcium and ethylene glycol solvation, which meaning that we have a blue elephant and a pink elephant. And we should be able to fit them equally with the exact same model here. Chlorite will not change, halite will not change, kaolinite will not change. These 16% smectite will change. Kaolinite, halite, nothing will change. Here we will have a change from the smectite component. And here with halite, 5% smectite and 10% chlorite, essentially no change is expected. So what we will change, going from calcium air dry in this case to calcium and ethylene glycol solvation, will be this fraction of smectite here and here. And I'm able, just by changing this smectite component from calcium air dry to calcium after ethylene glycol solvation, to go and to fit both the blue elephant and the pink elephant. So this is just to bring additional constraint, if possible, independent. So here I have 2 independent constraints from X-ray diffraction. But if you are able to work with Toshi, and you are interested not in the interstratification of this type of layer, but in interstratification of polytypic fragment, for example, it will be able to tell you that I have observed this and that type of polytypic fragment, and these are the 2 types of polytypic fragment you want to interstratify. The blue one and the red one, not the blue one and the green one, the blue one and the red one. Yes?
Explain it clearly discussed.
Yeah, so I will stop here. I think all other examples are just different ways to exemplify different structures, different ways to do that. All these are exactly the same. And what I would like you to get from that talk is that position may not be sufficient. We've seen that. You need to include not only position of the diffraction peak, but also their profile. there is a lot of information in that profile and intensity distribution about Bragg's peak. And it is possible to get that information for a precise identification of your mineral. Here I showed you an example just of interstratification of layers having different layer-to-layer distances, but you can do the exact same thing for interstratification of different polytypes. You can do the exact same thing for even in the presence of turbostratic, which means 100% random stacking. All this, you can get precise structural information from natural samples. Not saying it's easy, saying it's possible. And probably, yeah, last thing is that, again, to emphasize the importance of independent constraints. Independent constraints could come from high resolution TM, it could come from X-ray absorption spectroscopy, it could come from water absorption isotherm, it could come from molecular simulation, it could come from any other technique, experimental or computational. But everything else you can have would help to constrain the data you have and your interpretation. And with that, I will take any question. Thank you.
Do you have any advice if you're looking to do X-ray diffraction on complex mineral mixtures where you're actually caring about what kind of cations may be interchanged on the structure? So you have a complex mixture and you're looking to see from a geochemical perspective, did this react? Did this not react? How would you approach that in an X-ray perspective, or would you basically just use the X-ray diffraction to start with? Here's what it could be. We're still going to make everything homoionic, and then go back and maybe look at that initial pattern and try and guess what was there after making everything homoionic. Like, would you run your sample kind of as received first, and then go through the processes that you've talked about?
Getting information about what is actually the nature of cations in your smectite, because this would be probably the question, I guess, will be extremely complicated from X-ray diffraction point of view. One simple reason, and there are more complex ones, but one simple reason for that is that what X-rays are seeing is they are seeing essentially electrons, which means that they will see exactly the same thing looking at 2 sodium or 1 calcium. They will see 20 electrons, period. And differences you may expect is too minor to be able to be measurable. So I don't think this, I would probably use X-ray diffraction in that case to try to quantify how much layers are containing exchangeable cations, but probably try to assess the nature of these cations from different techniques like cation exchange capacity and measure of exchangeable cations, things like that. Again, most of what I would do in this case would be to use complementary techniques to be able to get the information you're looking for. I mean, yeah. I've been trying on my whole life to extract as much information as possible from X-ray diffraction data, and I know what I cannot expect from that data.
Thank you, Bruno. So your results about size dependence of elite peak you showed.
Yes.
It's a calculated one or experimental one?
These are calculated ones. I think you referred to this one. Yeah.
This calculated.
These are only calculated ones.
So probably you explained, but I couldn't catch up. But would you explain again why small size n equal 2.5 peak position is changed?
Yeah,
But
here
it looks not rational. It became rational.
it's not rational anymore. That's for sure. And one reason for that is that actually here, if you have to think about how is the diffracted intensity calculated, and intensity is calculated or generated. This intensity is just a convolution of what's called interference function here. Interference function here would provide peaks that are sharp or broad depending on the size, but position is always the same. And after that, you have a convolution by Lorentz and polarization factor, which is essentially steadily decreasing for.
And I think but peak around 20 degrees. It's also around 20 degrees.
Yeah. Yeah, and this
So
is
it's not due to the Lorentz factor effect.
This is just because what you have. So you have the Lorentz and polarization factor. Lorentz and polarization factor is steadily decreasing from low angle region to high angle region. But after that, you have what we call structure factor here, that essentially contains the motif of the unit cell, how many atoms of what nature are where in my structure. And this one is actually modulated and strongly decreasing in this low angle region here. So peak is going uphill. Then it's going back up again and low and down again in this region. So this one is moving uphill also, but it's moving uphill to the high angle side, and the other one is going uphill, going to the low angle side.
I understand. So probably this is just a damping effect.
Yeah.
But in general, naturally, so it's such pattern that we observe because it is in naturally, so n is not so fixed.
Yeah, the problem is that usually when you have this kind of size, you obtain very low intensity and broad peak, but this is essentially what we are doing when looking at these samples here. And here we may observe this exact same type of patterns. They're not periodic because in this case, the main effect would come from interstratification, but you will have the exact same effect here because we have extremely broad peaks, especially if you're looking at the collinearity, like you have extremely broad diffraction peaks. So you have also in this case shift from ideal position.